Welcome. So as mentioned, I will be presenting our research on the reconstruction of bed echolocation scan patterns using convolutional sparse coding. This research comes from a combination of current topics within our research group. We develop sensor systems with a specific focus on ultrasound. An application of ultrasound sensing was found in the analysis of bed echolocation, more specific, a pellet bat's hunting behavior. When a pellet bat is hunting, it can steer its beam and it can broaden or make it more narrow to locate a prey. A second line of research is focused on the automation of firmware development by using a model-based framework. This framework has recently been extended by the ability to automatically generate firmware for compressive sensing purposes, starting from a defined Nyquist conform timing model. This has been developed for a variety of heterogeneous systems on chips, such as STM32MP and Beaglebone Black. So it's modular, model-based. So for the introduction, to analyze the hunting behavior of a bat, in previous research, an array of 64 ultrasound microphones was captured at 450 kilohertz. These microphones were placed on a slightly rocky surface with a 3D printed scorpion to serve as a prey. From this microphone data, as displayed there, that's the microphone array, we can calculate the focus of attention of a bat. This is actually the center of mass of the beam from the bat. And then from that, a scan pattern can be calculated using the intensity on the microphones. So acoustic monitoring, as this is the use case of, is typically done in remote settings. And remote settings bring forth several challenges, such as battery lifetime. Battery lifetime has implications on the longevity of your captures. To lower your, this is a trade-off with the amount of data you can actually transmit or capture. And for these use cases, mainly specific firmware development is applicable. So to tackle this challenge, we have looked at convolutional sparse coding to deal with this trade-off. For this, we implemented pseudo-random sub-Nyquist sampling to, first of all, lower the amount of samples that we need. That way, we can increase the battery lifetime if it's implemented in a clever manner on firmware. You can have a longer sleep time of your chip and increase the battery lifetime without impacting your data quality due to the quality of your reconstruction using convolutional sparse coding. As a ground truth reference, we used the previously captured data, which was Nyquist conform, and used 64 ultrasound MEMS microphones at 450 kilohertz. On the right side, you can see a scan pattern from this ground truth reference. So the yellow blob is the beam from the bat, actually. From that, we calculate the center of mass as the focus of attention. So the point that the bat is actually kind of not looking at, but looking at with its sound. So then for a reconstruction of our sub-Nyquist sampling data, we use convolutional basis pursuit reconstruction, which is a variation on convolutional basis pursuit denoising, which is well embedded in the theory. So if we look at the first formula, Dm is actually in the traditional denoising, that's a set of filters, and Xm is your sampled signal, and then S is the vector into which your signal is reconstructed, or in the previous version filtered, and then you have the Lagrangian multiplicator to weigh on your minimization. So we modified this by sub-Nyquist sampling. So Xm is actually a sparse set of coefficients, and the rest is zero padded. Initially, the dictionary set was just a set of, in the frequency domain, a set of Gaussians covering the Avisian bandwidth. This did not provide sufficient results, so we looked at dictionary learning to improve the dictionary to provide a better match with the data to be sampled. And we will look at a validation of this method. And on the left side, we see the ground truth scan pattern. On the right side, we see the reconstructed scan pattern. To evaluate this, we looked at the differences between the center of mass, because the overall width of the blob is not really interesting to us. So we took 60 different sets of measurements on 4 different beds. And from that, we calculated, for the accuracy, we calculated the histogram of it. And we reach a median difference between the ground truth and the undersampling factor 10, which means we can throw away a fifth of the data, actually, 5 times the data. Not throwing away, but just omitting. And we reach a median difference of 9 centimeters of the focus of attention, and a standard deviation of 0.082 meters, so 8.2 centimeters. Then to verify the precision, we calculated a 2D kernel density estimate. And by looking at the center of mass of this blob, this is not a scan pattern, this is a 2D kernel density estimate. By looking at the center of mass here, we can see that it's just as for the ground truth, it's centered at 0, so it's as precise as the ground truth reference with a slightly lower accuracy. So my conclusions, we achieve a robust accuracy and precision with the proposed method, whilst being able to have 5 times fewer samples. And it's feasible for our use case of acoustic monitoring in the specific use case of bat echolocation. And it can tackle existing challenges in remote monitoring by allowing longer captures and having less frequent. For example, if you place it in the jungle, you have to go less often into the jungle, which can be nice. So for future work, we propose to expand the dictionary to more species of bats, more specific calls, and more animals in the environment you want to monitor. And to implement sub-Nyquist sampling on the previously mentioned generator framework for this use case. So that was all. Thank you for your attention.